Hi, and welcome to the Assembly Lines Podcast. I'm Chris Torrance. In today's episode, we're going to continue where we left off with my Apple II emulator, and we're going to clean up a few things that were not quite right, including the gamepad as well as the sound emulation. So let's get started. One of the more obscure modes on the 6502 processor is known as binary coded decimal. And this is a mode where instead of treating the digits of a number as hexadecimal, so 0 through F, instead you treat each set of digits as a decimal number from 0 through 9, and you disregard the higher hex values A through F. This is kind of an obscure and strange mode, and it wasn't really used very much on the 6502 or on the Apple II, except for one very crucial application. When I first fired up Snoggle on my emulator, it immediately crashed, and when I looked at the output in the console, it said that I hadn't implemented the SED, or set decimal instruction. Now, normally on the Apple II, as soon as it starts up, it calls the CLD, or clear decimal mode instruction, and from that point on, it's in hexadecimal mode. However, I couldn't figure out why Snoggle was actually switching to decimal mode until I realized that the problem was actually in the scoring for the game. Similarly, for Choplifter, when I was playing it, I noticed that when I got up to 9 hostages and then I rescued another one, instead of going up to 10, it just started printing garbage on the screen, and it eventually crashed. And what I came to realize is a lot of Apple II games actually use the decimal mode to keep track of scoring. This is because it made it a lot simpler to actually do the math. So instead of having that 9 roll up to an A, B, C, D, E, F, if you put it in decimal mode immediately before doing the scoring, then it would just roll from 9 up to 10. So let's take a look at how decimal mode actually works. In binary coded decimal mode on the 6502, each set of 4 bits represents one decimal character. So for example, here with the number 99, the high 4 bits, 1001, represent the 9. The low 4 bits represent the other 9. And this has some implications for how you do math. Now, the binary coded decimal, or BCD mode, only is applicable to 2 instructions on the 6502, the add with carry and the subtract with carry. Every other instruction simply ignores it. So if we do, say, for example, an add with carry, in normal hex mode, if I took the values 46 and 38 and added them together, I would get 7E. However, in binary coded decimal mode, I add those 2 numbers together and I get 84, which is what you would actually expect from normal math. So this is very nice for doing things like scoring in a game, but it makes it extremely confusing when you're actually trying to implement this in an emulator. I found an excellent website over on 6502.org which completely explained decimal mode on the 6502, and most importantly, it said what to do when you get illegal hex values. So for example, if we have the value 99 in BCD mode and we add 1 to it, it'll wrap around to 00, which is correct. However, if you have a value, say 9B, and you're in BCD mode, technically that is illegal, but the 6502 has to do something with that value, and I wanted to emulate it accurately in case there was any programs that were relying on that. So if we go back to the website here, there is an entire appendix about what to do with illegal values, and there are all sorts of pseudocode for how to handle these special cases, and you can see all of these down here. If we look at my emulator code and I look at my add with carry instruction, I now have 2 different branches. If I'm in decimal mode, then I'll just call this do add with carry BCD. Otherwise, I'll do my normal add with carry in hex mode. Add with carry in hex mode is pretty straightforward. You just do the addition, making sure to take into account whether the carry flag is set, and then you just set your carry flag, your overflow flag, as well as your zero flag appropriately. Now, for binary coded decimal mode, things are a little bit more complicated, and this is because we have to worry about these illegal hex values. So you can see here, we're doing the normal binary coded decimal addition, but now we have to add an extra step. If our ones digit actually wrapped around to the value 0xa, then we want to jump up by 6 values to get to the next tens digit. And this will handle illegal values. Similarly, for the hundreds digit, we do the same thing. If we did wrap around, then we go ahead and we add 0x60 to our value. And then finally, we also want to set the overflow flag as well as the carry flag and the zero flag. Now, one thing to keep in mind is there's some subtle differences between the 6502 and the 65C02. So the 6502 didn't worry about setting the zero flag at all, and it just ignored it for BCD mode. The 65C02 actually does the correct thing. And in my emulator, I just went ahead and decided to emulate this as if it was a 65C02. Similarly, if we look at the actual instructions on the 65C02, when I'm returning the number of cycles that an instruction took, it actually takes one additional cycle if you're in BCD mode for the add with carry or subtract with carry. And this is because it needs to properly set that zero flag. So when you're returning your cycle count for these instructions, you need to return the correct value depending on which mode you're in. If we scroll down to my subtract with carry, again, we can see that things are more complicated. If you're in hex mode, then you can actually just call the add with carry. However, if you're in BCD mode, then I needed to implement a completely new code path for that, and it's just as complicated as add with carry. So once we got all that done, then the binary coded decimal mode worked properly, and we were able to play games like Choplifter or Snoggle and have it keep score correctly. All right, so now that we've got BCD mode taken care of, let's go ahead and take a look at my gamepad support. In the last episode, I talked about adding support for gamepads and game controllers like this GameSir here, and I showed how you could implement all of the buttons as well as the thumb controls. One thing I forgot to talk about, though, was how to actually calibrate these joysticks. Now, if you have an old, say, TG joystick, like this one here, the joystick actually went all the way from 0 to 255 in both directions. And I have a diagram of what this looks like. So in the upper left, we go from 0, 0 all the way down to the lower right, which is value 255, 255. The problem with a lot of these modern game controllers is the thumbstick actually is circular. And this is, I'm sure, more of an ergonomic thing where it makes it a lot quicker to dart around from left to right and top to bottom. And most games, at least most modern games, are perfectly fine with this because really they're all looking for just either negative or positive, and they don't really care about the values in between. It's just either on or off almost, or just left, right, or up, down. However, for an Apple II, this is actually a big problem. And I've fired up the Mech System Inspector disk here, and we can go ahead and see what I'm talking about. If we do the joystick paddle test, you can see that we can move around here, and we can kind of go around, and if I go all the way to the left, I get a value of 0. If I get all the way to the right, you can see I get a value of 255. So that's all going well. Similarly, if I go all the way to the top, I get a Y value of 0. And if I go all the way to the bottom, I get a Y value of 255. However, what happens if I try and go into the corner? Here, I get stuck. I can get to about 30, 31, but that's as far as I can get for X and Y. And then let's try the opposite corner. And here I can get down to about 225, 227. And so what ends up happening is you have this circle, and that's the range of a normal thumbstick. Now, for a lot of Apple II games, that's going to be fine. It doesn't really matter because it's actually like modern games where it just cares whether you're left, right, up, or down. But there are a few games where it's going to matter a lot. One example is Olympic Decathlon, where you're trying to do the shot put event. And in that one, it actually has you start the joystick at 0, 0, and that's how you indicate to the computer that you're ready to actually start the event. So we would never actually be able to play this game with this thumbstick. I wanted to try and fix this in my code, and I went through a lot of contortions, but I finally came upon a solution which I think works. Let me bring up a diagram of what I'm talking about so we can explain it. So the red circle here is a representation of the thumbstick's range, and then the black outline is a representation of, say, my TG joystick. So it goes from 0, 0 all the way to 255, 255. The thumbstick goes from -1 to +1 in both directions, but in the corners, it gets stuck. What I decided to do was actually just apply some math to essentially scale this range. So for example, if the joystick is up here at, say, a value of -0.8 and -0.8, I need to actually convert that to the value 0, 0, rather than just getting some arbitrary in-between value. And then as you get closer to the axes, the x-axis or the y-axis, I want that scale factor to actually go away, because in that case, it's actually correct. So if we take a look at my code, the formula that I came up with is actually just based on that triangle that I had drawn in the diagram. And all I'm doing is I'm taking the ratio of either the x or the y value, whichever one is larger, and I'm dividing that by the length of the hypotenuse. So square root x squared plus y squared. And then I'm just applying a small fudge factor of 0.95, because I found that a lot of times if you didn't do that, you wouldn't actually be able to get to 0 to 255. So you need to slightly decrease the range of the thumbstick. So looking back at my diagram here, what I'm doing is I'm just taking the ratio, say in this example, of this y length to my hypotenuse length, and I'm dividing the corresponding x and y values by that ratio. And so that'll take this arrow and expand it all the way out until it meets the edge right here. Now I put together a little 3D representation of what that formula looks like, and that's here. So if we look at this diagram, this is the x-axis of the thumbstick here from -1 to +1. Over here is the y-axis, and then finally this value here, which goes from 1.0 up to 1.414, is this scale factor. And I can kind of rotate this around so you can see, basically, if I'm on the x or y axis, my ratio is just 1, but as I get closer and closer to the diagonal, then this ratio approaches the square root of 2. And this just takes all those values and stretches them out into the corners. So now that I've re-enabled that in my code, let's go ahead and save it, and we'll try it out in my emulator. I'll load up my mech disk again. And once it's started, I can start the joystick test. And now with that enabled, so again, I can go left, right, up, down. But you can see now, if I try to go all the way into the corner, I can actually get all the way there. So now I'm at 0, 0. And then similarly, if I go down in this corner, I can get all the way to 255, 255. And because that scale factor is pretty subtle, I actually didn't really notice any kind of loss of sensitivity. It's actually still pretty responsive, and I can almost dial in any value that I want. Now, it's still maybe not as great as a TG joystick, for example, where you just had a much larger range and you didn't have to worry about that kind of weird circular corner effect. So if you're going to play a game on a real Apple II, this is definitely preferable. However, if you're playing in an emulator, it's nice to be able to use a modern thumbstick and a game controller. Now that we've got that taken care of, let's go play some games and see if we can figure out what was going wrong with my sound. If you recall from last episode, I had gotten the sound working pretty well in my emulator, and it was great for simple tones and music. However, there were still a few cases where it was falling apart, and one of those was Castle Wolfenstein. And the answer turned out to be a lot more subtle than I expected. Let's take a look at what it sounded like last time. I'll go ahead and fire it up. And while it's loading, I'll just point out a couple new features that I've added to my emulator. I added a button down here for uppercase, and this will just force all the characters to be uppercase before they get sent to the emulator. And this is just because I kept forgetting to hit the caps lock key. And then over on the right-hand side, I have a running display of the Apple stack. The stack on an Apple II starts at location 01FF and goes down in memory from there. So the higher memory addresses here are the oldest part of the stack, and then the newest parts of the stack, or the things that most recently have been pushed on, are down at the lower memory addresses. And you can see that while the game is running, this is being heavily used. However, it's never actually returning to any of these other addresses. This is the stack address here. Here is the actual location that was pushed onto the stack. So when a return instruction occurs, this is where it's going to jump back to. And then where possible, I've remembered the instruction that caused that stack push. So for example, there was a jump to a subroutine at A851, and then this is the return address for that. Here, it's lost track of what that instruction was, probably because something was pushed or pulled onto the stack. You can see down here, it's actually recorded a push of the accumulator onto the stack. So that would be a PHA followed by a PLA, or a pull accumulator off of the stack. Down at the bottom here, I actually have the 0 page of the Apple II's memory, and this is also being dynamically updated, so you can see what values are changing and how quickly. What I'd like to do is eventually be able to color code this so it would show, say, the most recently changed values in red, but I haven't gotten around to that yet. Now we've got Castle Wolfenstein running. Let's go ahead and listen when I fire my gun with the L key. Okay, that definitely does not sound correct. And as we saw last time when we tried this in Virtual 2, it sounds much better like a real gunshot. I really couldn't figure out what was wrong because everything else seemed to work properly. However, one of my YouTube subscribers who goes by the initials XOT, I'm not sure if that's really XOT or Zot, he also has an emulator and his Castle Wolfenstein was working properly. When he went and looked at his emulator code, what he found was surprising. The only difference was that his emulator was actually doing a proper job of handling floating bus noise. If we go over to Virtual 2, I have Wolfenstein running in this one, and I put a breakpoint where the code accesses the C020 soft switch. And you can see that when the guy fires his gun, it almost immediately loads the accumulator at that location. So what is C020? Well, it turns out that's actually the cassette output for the Apple II, and we're not actually using the cassette. However, when the Apple II does its memory refresh of the video memory, these values can actually linger for a short amount of time on the data bus. And when you do a load accumulator from a soft switch that isn't actually hooked up to anything, you'll actually pick up this floating or random bus noise. This also happens if you do a load accumulator from the C030 soft switch, which is actually the speaker address itself. So when you do that, it toggles the speaker, but it actually does load the accumulator with a value. And it turns out this is also one of these floating random noises, which aren't actually random because they come from the video memory. Now, I have kind of a problem because in my emulator, I'm not really doing the proper video signaling. Unlike the 6502 circuitry, I'm not actually loading all of those video values onto the address and data bus. Instead, I'm just loading them directly from my stored memory and blitting it right to the screen. Although my emulator isn't quite doing things properly, what I decided to do was actually just go ahead and put in some random noise. Let's go over to my code now, and if we go over to my motherboard file, you'll remember I have this memget routine, and anytime someone requests memory from the 6502, it goes through this routine to make sure that I'm not accessing a soft switch. And now I had to put in support for, say, this C020 address as well as C030. And let me uncomment these lines here. What I'm doing is I'm simply saying if you access one of these soft switches, I'm going to go ahead and fill in that address location with just a random value between 0 and 255. And I do the same thing for the C030 address, and then I go ahead and actually click the speaker as usual. Now that I've got that code saved, let's go back to my emulator. Let's go ahead and load up Wolfenstein now, and I'll turn off the speed limiting so we can boot quickly. Okay, let's put the speed back on, and here we are, and let's go ahead and fire our gun. Okay, so you can see that actually sounds a lot better, and now I've run out of bullets. One other thing I noticed is the walking actually sounds a lot better. It was a little strange sounding before, and now that sounds good. Let's try our gun again. That's good. One other thing I noticed that had been puzzling me is when I went over to a chest, normally if you try to search that and then you fire your gun, it actually cuts time off of it so you can open it more quickly. In my original code, when I didn't have that random number generator at C020, it was always taking the same amount of time to open the chest, and firing my gun didn't have any effect. I thought that was kind of weird, but I really didn't think it was actually a problem. However, now that I've put in that random number, now everything works properly, including the time that it takes to open chests. I have a feeling that it's using that C020 location for a lot of different things. We already saw that it's using it for the sound effects as well as the chests, and I bet it's actually using it for the frequency of how often the SS show up in your room. It was actually funny because after XOT posted that comment on YouTube and I posted my response saying that it had fixed my problem, Nelson Weissman also posted and said that his emulator was now fixed as well, and so he was grateful for the same fix. I'm not sure what the moral of the story is. I guess if you're writing an emulator, you really have to look carefully at everything that the real hardware is doing and try to emulate it as faithfully as possible. And I'm sure I'll run across more of these things in the future. Now that I have the sound implemented properly, there's one last test that I want to do. Someone recommended that I try out the Halley Project game as an example of what some sophisticated sound effects on the Apple II sound like. Let's go ahead and boot that now and we'll see that. I'm going to turn off the limit speed. And this might be kind of loud, so watch out for your speakers. I'm not sure how that sounded on your end, but for an Apple II, that was pretty much state of the art back in the day. And I think my emulator is getting close to approaching that sound. I would say it's not quite perfect yet, and I still might need to do a little bit of tweaking. There's a few more things that I did in the code to try to improve the sound. In addition to that random noise which fixed Wolfenstein, I also went back to my oscillator code and I extended my work array a little bit because I noticed it was wrapping around. And then I also added in a quick check to see if we're starting a brand new sound. So if it's been a long time since we did a sound, the trouble with the way I implemented it is it would just start that sound anywhere within this 128,000 buffer. And so it actually might take about a half a second before my process down here would actually loop around and pick up that signal. So now, if my delta in the 6502 cycle instructions is large enough, I just assume that I have a brand new sound and I start it right away. I hope you enjoyed this episode of the Assembly Lines podcast. We took a look at how binary coded decimal mode works on the 6502 and how we could emulate it. We also took a look at the gamepad and how we could improve the emulation for the thumb wheel on that. And then finally, we looked at my sound emulation and figured out what was wrong with it so that the sounds on Castle Wolfenstein would work correctly. In the next episode, I'm hoping to take a look at how to add write support to floppy disk images. In the meantime, please hit the subscribe button down below. And if you'd like to become a Patreon subscriber, I'll have a link in the show notes for that. Once again, thanks for watching.